We have these two functions, f and g, and we assume that f and g belong to the L2 space, where omega here is 1D interval, a comma b, this closed interval. Then the linear combination of this form, C1 times f plus C2 times g, also belongs in the L2 function space, where C1 and C2 are real coefficients. We are going to write a proof for this result. We take the norm of this linear combination, the L2 norm squared, as the integral from a to b, C1f plus C2g, these are real valued functions, dx. And this is C1 squared f squared plus 2C1 C2 fg plus C2 squared g squared dx. I can break this integral, so it's C1 squared integral from a to b f squared dx plus 2C1 C2 integral from a to b fg dx plus C2 squared integral from a to b g squared dx. This is FL2 squared plus 2C1 C2 integral from a to b f times g dx plus C2 squared norm of g in L2 squared. Now I use Cauchy-Schwarz inequality to bound this term here. I can bound this integral. This is bounded by the product of L2 norms of the functions f and g. And this is this right hand side is simply C1f plus C2g in L2 squared. Oh, sorry, the norm, so no, this is not correct. So this is just C1 times the norm of f in L2 plus C2 times the norm of g in L2. And this is squared. So I have the norm C1f plus C2g in L2 squared, and this is bounded by C1 norm of f in L2 plus C2 norm of g in L2 squared. So from here I have that an L2 norm of the linear combination is bounded by C1 times the L2 norm of f plus C2 times the L2 norm of g. And because I know that f and g belong to the L2 space, I have that the norm C1f plus C2g in L2 is, so this is finite. So from here, the linear combination of the functions f and g also belongs to L2 space, and this concludes my proof.